The second part of the design for the water reticulation system, it will be calculating the head loss. You know that there are requirements in terms of the minimum and maximum pressures in the water reticulation system. You will need to first get the water pressures of the existing main at the locations where you're going to tie in your water reticulation system with the existing. You will need to request for the information of the 24 hours pressure record chart to get the existing pressure. You're going to expect the frictional resistance of the pipelines that will lead to the head loss in terms of the pressures within the water reticulation system. The longer the pipeline, normally the head loss will be larger. Now, how do you calculate the head loss? You may refer to the Hazen William formula to determine the head loss. These are the equations to calculate the head loss for the circular pipe flow. If you search for the Hazen William formula, you will get two different equations. Some references give you this, while others giving you this. The two equations are Hazen William formula, only that they are in the functions of different parameters. This formula is in the functions of the flow rate, whereas these formulas, it will be in the functions of the velocity. For more details about Hazen William formula, you may refer to this guideline, Design Guidelines for Water Supply Systems, published by Malaysian Water Associations in 1994. The equations for Hazen William formula are given here in the mode of velocity, flow rate, as well as the head loss. This slide shows the relationships of the two equations for the head loss given by the Hazen William formula. This is the equations of the flow rate, which is in the functions of the hydraulic gradient. The hydraulic gradient is calculated based on the head loss per unit length. Now, if you substitute this into the equations, rearrange the equations, you will get this. Similarly, if you derive the equations from the velocity flow, incorporating the hydraulic gradient into the equations, rearrange the equations, you get this. You can simply convert this into this by having the Q equals to VA. Velocity multiply the areas of the pipe, where the area is calculated on basis of the internal diameters of the pipes. Substitute the Q and A into the equations, rearrange it, you get this. So in another word, to calculate the head loss, you can use either this or this. Ultimately, you know that we are more interested with the velocity, which needs to be within an acceptable range of 0.3 meters per second to 2.0 meters per second. The velocity cannot be less than 0.3 meters per second in order to reduce the depositions of the sedimentations. This requirement can be obtained from the Uniform Technical Guideline, Water Reticulations and Plumbing, produced by the SPAN, Suruhanjaya Perkhidmatan Air Negara. For some reasons, the guideline for the submissions of water supply and internal plumbing system for development scheme does not specify the minimum and the maximum velocity for the water reticulation systems. To be safe, you may adopt the requirements given by the Uniform Technical Guideline, Water Reticulations and Plumbing. It is also noted that the limitations of the Hazen William formula. In most of the references, they specify that the Hazen William formulas is not really accurate. For more accurate estimations, many references recommend these two types of formulas: the Colebrook-White formula as well as the Darcy-Wells-Bash formula. These formulas are more accurate and suitable for all pipe size and flow range. Nonetheless, the Hazen William formulas can still be used in our reticulation system, as normally we use 150 mm diameter pipes for the water reticulation system. In terms of the pipe size, 63 mm pipe and 90 mm pipes are commonly used. If you refer to the Uniform Technical Guideline, the minimum pipe size it will be 100 mm. Now, the limitations of the Hazen William formulas is that it is not suitable for the pipe diameter less than 50 mm. Our water reticulation systems is well above the 50 mm diameter. As for the velocity exceeding 3 meters per second, the Hazen William formula will not be suitable. However, the requirements it will be between 0.3 meter per second to 2.0 meter per second, which is way below the 3 meters per second. The point here is the Hazen William formula can still be used in the water reticulation system, as the diameters of the pipe commonly adopted are greater than 50 mm and the design velocity are normally not exceeding 3 meters per second. The other limitations about the Hazen William formula is that it is not accurate when the coefficients for the Hazen William formula is substantially lower than 100. The Hazen William coefficients is governed by the pipe materials. Normally, Tata iron pipes is being used. The Hazen William coefficients is larger than 100. That can make the Hazen William formulas inaccurate. Or HDPE pipes, which is also larger than the 100. Therefore, the Hazen William formulas can still be applied for a typical water reticulation system. According to this reference here, the Hazen William equations is most accurate for pipe size and velocity typically found in the water supply practices. It may be inaccurate and conceptually incorrect as per remark by most of the researchers. However, when come to the industrial practice, the Hazen William formulas is easy to use and it gives an acceptable levels of accuracy as long as its diameter is not less than 50 mm, the velocity not more than 3 meters per second, and the Hazen William coefficients not substantially lower than 100. Having this said, you can comfortably use the Hazen William formulas for you to do the calculations. Next, we look into how we're going to use these formulas to calculate the head loss. There is a factors of 10.7 multiplied with the pipe length, which you can measure from the plan, and then the diameters of the pipes, which is normally 150 mm or at minimum 100 mm depending on the specifications given in the plan, and then the Q is the flow rate which you have calculated previously. Make sure you do a proper conversions from million liters per day into meter cubes per second. There are at least 3 scenarios here: average water demand, peak water demand, average water demand plus the fire hydrant water demand. Next, it will be the Hazen William roughness coefficients. You may refer to this table here. Or if you are referring to the design guideline for water supply system, the Hazen William coefficients, you can get it from the table 14.14. Substitute the value into the equations, you get the head loss. Alternately, you can use these equations. The calculated head loss shall be the same as this. Only different parameters is being used. At the same time, you will need to compute the velocity by taking the flow rate for all these three conditions divided by the internal areas of the pipe. Check the velocity within the range of 0.3 meter per second to 2.0 meter per second. Coming back to the calculated head loss. Remember, previously we mentioned about 24 hours pressure record chart. This is an example of the water pressure chart. You can see the water pressures are fluctuating along the day. There will be minimum pressure and the maximum pressure. You can use the minimum pressures to minus with the head loss to determine the residual pressures within the pipes, and also minus the maximum pressure with the head loss to determine the range of the pressure of your development areas. Make sure the pressures are within the limits. Now, if you find the pressures is way lower than the minimum pressure, you will need to propose mitigations, such as providing high level tank or booster pumps to increase the pressure. Now, if the pressure is going way beyond the limit, you have to come up with a measure to reduce the pressure in the system, such as providing the pressure reducing valve. The calculated head loss using the Hazen William formula is in meter as the unit. If necessary, you may need to do some conversions in terms of the pressure. 1 meter pressure is equivalent to 0.098 bars. This equation represents the water pressure calculated by minusing the average pressure at the tie-in point with the head loss. Measure the water pressure for all the cases falls within the acceptable range between the minimum pressures and the maximum pressures.